I'm Dan Berch from the University of Virginia, here to start the next panel session, which is entitled The Role of Executive Function and Language in Learning Disabilities. Okay. All right, our first presenter is Philip David Zelazo. He's currently the Nancy M. and John E. Lindahl Professor at the Institute of Child Development, University of Minnesota. His research has helped shape current scientific understanding of executive function and its development, including the key roles of reflection, rule use, hierarchical complexity, mindfulness, and emotion, especially hot versus cool EF that he'll describe in a minute. This work has led to the design of widely used standardized measures of EF skills, for example, the NIH toolbox measures of EF, and to the creation of effective interventions for promoting the healthy development of EF in early childhood. The title of his talk is Development of Executive Function Skills in Childhood, Implications for Learning and Learning Disabilities. Since we're running a little late, I've asked him to just present the first half of his slides. They thought I'm serious.
Okay, thank you. I'm going to give a brief overview of the way in which we think about executive function, and I'm hoping that the implications for learning disabilities will come out in the discussion. So executive function refers to a set of attentional skills or ways of using attention that are involved in the goal-directed control of just about everything else that the brain does: thought, emotion, motivation, action. These are processes that are related to but different from what we normally mean by the term intelligence. In contrast to intelligence, executive function has more to do with taking what you know and putting it into practice, actually executing on the basis of your understanding. Executive function skills are typically invoked when we encounter a problem. We get by pretty well on autopilot, as you know, for many things. But when we run into an obstacle, we can switch out of autopilot into a more intentional, top-down kind of mode. And that's when we draw upon our executive function skills. Executive function skills, we believe, develop in large part as a result of the development of reflection. And I'm going to say more about what reflection means. In general, though, reflection changes one's perspective, providing what we call psychological distance from a particular situation. And just as physical distance provides a panoramic view and reveals various pathways to an end, to an objective, psychological distance shows us the range of possible responses that we have in a particular situation, and it puts us into a position to select among them. I mentioned executive function skills can be thought of as ways of using attention, including using it flexibly, selectively, and in a sustained way over time. And in fact, we typically measure executive function skills behaviorally in three ways that correspond to these different ways of using attention. We measure cognitive flexibility, for example, typically using some sort of task switching paradigm where, depending upon the cue, you have to attend to one aspect of a stimulus or another. In short, you need to be able to look at one thing and think about it from multiple points of view, as when, for example, you take somebody else's perspective on a situation and it differs from your own. Inhibitory control refers to the suppression of attention to distracting information. And we also use the term to refer to impulse control, suppressing responses of a non, for example, visual or attentive nature. And working memory refers to the maintenance and manipulation of information, or in short, holding information in mind and using it, as it were, in a kind of top-down way to guide your intentional responding. There's another distinction that we've focused on in our research I'll just mention briefly, and that's the distinction between cool and hot executive function. Typically, when people talk about executive function, they're talking about cool executive function skills, which are usually assessed in relatively abstract, decontextualized, offline ways. And these skills depend on neural circuits involving, to a large extent, lateral parts of prefrontal cortex. In contrast, more ventral and medial parts of prefrontal cortex play a key role in hot executive function, which is a form of top-down regulation that is invoked in situations that are motivationally significant. And typically they're assessed in paradigms where one has to be flexible in their reappraisal about whether to approach or avoid a concrete stimulus. And so here's an example, a classic example of a hot executive function measure, the classic marshmallow task pioneered by Walter Mischel and his colleagues, delay of gratification. In one version of this task, children are simply given a choice. Would you like a smaller reward now, like one candy now, or would you rather wait and have 2 candies when it's time to go home? And in one study with Angela Principe, we presented this task to 3- and 4-year-olds, and we did it in 2 different ways. The way I just described, which we called delay of gratification for self. Would you, the child, like 1 now or 2 later? But we also asked these kids, okay, now it's my turn. I get to choose. I can have 1 now or 2 later. What do you think I should do? And what we found is that 3-year-olds typically gave very good advice to the examiner and said you should wait and take the larger reward, but they themselves opted for the immediate smaller reward. There was no difference between these 2 conditions in the 4-year-old group, suggesting that they split the difference between the benefits of a larger delayed reward and some short-term return. A paradigm that has been fairly widely used to assess cool executive function in childhood is the dimensional change card sort, in which children are shown either in a tabletop version like this or on a tablet or something, 2 target cards and test cards on every trial that would be sorted differently depending upon whether you were sorting by shape or color. And children are instructed on each trial, for example, first we're going to play the shape game, cars here, flowers here, here's a flower, where does that go? And then on subsequent trials they're told, we're not going to play the shape game anymore, it's a new game, it's the color game. If I show you a red one, I want you to put it here, a blue one, I want you to put it there. And regardless of whether you start with shape or color, 3-year-olds typically get stuck on that first way of treating these stimuli. And they do this, so they continue to sort by the first dimension, they perseverate, as we say. And they do this despite demonstrating knowledge of the new rules. So when you ask a child, you say, okay, we're playing the color game now, right? And they say, right, and you say, so where do the red ones go? And they'll point to the correct box. Where does this red one go? They'll treat it in terms of its shape, so they'll sort it incorrectly. Here's a very brief clip that I have.
If it's blue, put it here. If it's red, put it here. Here's a blue one. Okay, so now we're going to play a different game. We're not going to play the color game anymore. Now we're going to play the shape game. And in the shape game, all the stars go here, and all the trucks go here, okay? Stars go here, trucks go here. Where did the stars go? And where did the trucks go? Excellent, okay. Stars go here, trucks go here. Here's a truck. Stars go here, trucks go here. Here's a star.
Okay, so you see this phenomenon, which not incidentally is a classic failure of executive function going back to the long history of neuropsychological work on this construct. Patients with damage to prefrontal cortex in card sorting tasks like the Wisconsin card sorting test also show that kind of dissociation between some access to the knowledge that's required, but difficulty translating that knowledge into behavior. More recently, we've tended to use the Minnesota Executive Function Scale, or the MEFS. This is a version that's designed as a computer adaptive tablet game for convenient school use. It takes about 4 minutes or so, I should include this disclaimer because my colleague Stephanie Carlson and I and the University of Minnesota are entitled to royalties from the sale of that test. But using that test, we've been able to collect data, for example, from now over 20,000 individuals in 8 countries and 7 different languages, and those de-identified data contribute to the norms that support the interpretation of the MEF's performance in any individual case. And with these data, you can see that, as we suspected, there are continuous and fairly rapid improvements in performance on this task during the preschool years. Performance continues to improve beyond that. It reaches a peak in young adulthood about age 25 and then begins a slow, gradual decline into senescence. There's been a lot of interest in the development of executive function in recent years for reasons you're probably familiar with. Executive function skills predict learning and achievement and adaptation, as we've heard here. And in some cases, they have been found to do that better than IQ, and they've also been found to predict across fairly long time frames from early childhood into adulthood, for example. Problems with executive function are associated with a wide range of clinical conditions with childhood onset, such diverse conditions as ADHD, autism, conduct disorder, and others. Importantly, there's evidence that executive function skills can be improved with practice. I'm going to end with a brief mention of that. Executive function skills protect against risks associated with poverty as well. In some work we've done with homeless children in the Twin Cities and other work that Ann Maston, my colleague at Minnesota, has done, we found that, that those children who are growing up in challenging circumstances, who are spending time in a homeless shelter, and therefore are at risk for academic failure, well, of course, not all of them fail academically, and executive function seems to serve as a protective factor against the damaging effects of economic disadvantage and other forms of disadvantage. Why does executive function predict key outcomes? We've argued that executive function skills provide a foundation for learning and adaptation across a wide range of situations. Perhaps especially they're essential in learning in a classroom environment where there is considerable structure and a lot of demands are placed on children's emerging executive function skills. These skills are required for children to pay attention and avoid distractions, of course, to remember rules and instructions and questions, to resist impulsive responses, to manage emotional reactions, including upregulating motivation, downregulating boredom and frustration, and so forth. Children with better executive function skills have been found to learn more efficiently. There are several examples, but that paper cited there was one where people received a certain amount of instruction around theory of mind, and those children who had better executive function skills got more out of that bout of instruction. Other colleagues have found that children with better executive function skills show greater gains in math from kindergarten to first grade. Children, in contrast, with relatively poor executive function skills may be distracted, they may fail to remember what the teacher said, they may act out in class, generally learn less effectively. Of course, they may directly or as a secondary consequence be more likely to get into trouble, to get suspended, or even expelled. So, back to the good news that it is possible to train executive function skills, and I believe there's a reason for optimism regarding the generalizability of what it is that's trained. Executive function skills, we believe, therefore, are modified by experience, of course, and we've heard this today. The brain is really an inherently adaptive organ. I like to say we grow our brains in particular ways by using them in particular ways. In other words, the development of the brain is, to some extent, unconstrained and influenced directly by the nature of the experience or practice that an individual engages in. So when we activate particular brain networks and use them, they adapt, they become more efficient. as a result of processes like the pruning of extraneous synapses, the myelination of axons, the sort of stuff that we heard this morning. This is true across the lifespan, but there are periods, evidently, of relative plasticity associated with relatively rapid behavioral change in different domains. You can see this in the development of the perceptual systems, and arguably also in the case of executive function, which develops very rapidly during the preschool period, suggesting that that may be a particular window of opportunity for interventions to occur. Of course, it's also easier to build good habits around attending intentionally when you don't first need to break years of bad habits. And a boost in children's executive function skills, even a small one, just prior to that transition to kindergarten could make a big difference in children's lives, initiating a cascade of positive events rather than a cascade of negative events. So children with a boost in their executive function skills may show increased motivation to learn. They may be in a better position to develop good relationships with teachers, decrease in problem behaviors, and so forth. There are also economic arguments for a greater return on your financial investment associated with early interventions rather than later interventions. In general, effective interventions targeting executive function, I believe, provide children with opportunities to practice reflection on their executive function skills. So there's a metacognitive component as well as practicing specific executive function skills and learning, therefore, by doing. So to practice reflection, what we're talking about is helping children to understand when they need to switch out of autopilot and into that more intentional mode that I mentioned. So we provide children with opportunities to say, okay, this is a tough problem. Don't just assume you know the answer and dive right in. Pause, consider your options, reflect, become aware of your executive function skills, recognize when and how to deploy them. But also directly practicing paying attention, thinking flexibly, keeping information in mind. It's clear from this research that these intervention efforts need to be sensitive to the developing skill level of the child, right? So they have to continue increasingly to challenge children's developing executive function skills. I'm going to just end by telling you about one study that we published a couple years ago in Developmental Cognitive Neuroscience, a series of 3 studies with preschool-aged children, about 3.5 years of age, who failed the dimensional change card sort in the way that the girl did in the video that I showed you. And we took those children and we randomly assigned them to receive reflection training or some other active control condition. We had a number of them across these different studies, including using the very same context in which we delivered reflection training, but doing it in a slightly different way, with merely corrective feedback, but without that key reflective training aspect to it, in which children are shown how to pause and step back and use language to talk their way through a problem. And then children were tested on that task using different shapes and colors, as well as other tasks to look at transfer, including a measure of false belief, which we didn't train at all. Of course, post-training performance was assessed by an evaluator who was blind to condition and all that. Here's a little bit more about the reflection training condition. This was in one of those studies. It was a very brief 24-minute intervention where the examiner worked with the child and basically served as a role model to illustrate these processes of pausing, stepping back, taking the big picture, selecting, and then responding. And what we found across all 3 of these experiments is that in each of them, about half of the children, all of whom had failed this task to begin with, now passed this task. We also found significant improvement in trained children in their performance on that theory of mind measure. So that's a task where children are shown something, a series of such tasks, like a Crayola box and they say crayons, and you open it up and it's got something unusual in it, like sticks, and you close it up and you say, when I first showed this to you, what did you think was in it? And typical 3-year-olds often say sticks, right, even though they thought that there were crayons in it initially. And if you say, what would your friend think if they came and saw this for the first time, looked at it from the outside, didn't look inside, they say sticks. Well, children who were given this reflection training were more likely to understand that previously they thought there were crayons in it, now they understand there are sticks. Or they know there are sticks in this box, but their friend would believe that there are crayons. In that same study, we recorded scalp electrical activity before and after this brief intervention, and we found that there were indeed correlated changes in children's neural activity as measured using EEG and looking at ERPs. And we were particularly interested in a component that's critical, evidently, in executive function processing, the N2 component, which seems to index the recognition that there's a problem, this trigger to switch out of autopilot and onto something else. So trained children not only did better, but there were correlated changes in their ERP amplitude for this critical component, and the direction of the changes was to push these children to look more like older children who spontaneously did well in this particular task. I'm not going to mention these other interventions except just to say that they're there. We also look at mindfulness as a way of supporting reflection training. This comes out of, in fact, this work that we did in homeless shelters, because there we found that some of these kids were so stressed, presumably post-traumatic stress problems, that they had difficulty engaging with us and benefiting from the reflection training. But the combination seemed to work particularly well. We also have begun to develop ways to take reflection training out of the laboratory and into classroom settings. For example, we have an intervention we've been working on for a couple years called Ready for Routines, in which it's a 2-generational approach in which parents and children collaborate in a kind of goal-directed way to reflect upon and refine daily routines, for example, around bedtime and mealtime. And I'm going to leave you just with these take-home messages. Executive function skills, I believe, are needed for learning and adaptation. Intentional learning and adaptation, not implicit learning, not perceptual learning. Executive function, as we know, it is different from IQ. It develops rapidly in childhood, predicts academic and other outcomes, and increasingly, I believe, research supports this claim that effective interventions promote reflection and provide opportunities to practice executive function skills. Thank you.
We were going to leave Q&A till the end, but this talk convinced me that in order to maintain that information and working memory, it'd be easier if you asked a question or two right after. So, Rob, go ahead.
Bill, what is the duration and frequency of the reflection training?
In the study with the ERP, it was a single intervention, 24 minutes. We didn't look at long-term changes. It was more of a proof of concept kind of thing. But incidentally, I wouldn't expect that a short-term intervention would produce long-lasting changes. Presumably, it's like physical exercise. You got to keep doing it if you want to maintain any gains.
Anything else?
One quick question about the N2 amplitude.
N2 amplitude, sure.
Is that something that you've looked at in isolation from a particular set of activities? I mean, we know what parents and educators and the public is up against in terms of, train your brain, consumer ready, do this, and your kid will be better at X, Y, and Z. Could you just reflect
Sure. We've looked at the N2, and many people have. It's a fairly widely studied component that seems to be associated with the detection of conflict or a problem, right? And as I say, that is the trigger to invoke our executive function skills. And so the efficiency with which we detect problems and then move on to the invocation of executive function skills to resolve the problem is associated with a reduction in the amplitude of the N2. And we've seen that in other situations across a wide range of ages. So the amplitude of the N2, the efficiency of it, a smaller N2 is associated with more efficient responding in those kinds of situations. And also, generally, the amplitude of the N2 in paradigms like a go-no-go task or something generally declines, but we have done some work where we measured a number of other measures of executive function, and we found that actually the development of executive function or executive function skill is more strongly related to the amplitude of the N2 than is age per se.
Okay. Thank you. Thank you, Phil. Our next presenter is Lee Swanson, who is Distinguished Professor and Pilloy Chair of Educational Psychology and Special Education at the University of California, Riverside, and Research Professor at the University of New Mexico. He is Editor-in-Chief of the Journal Learning Disabilities, and his own research focuses on working memory as it applies to math, reading, and intelligence in children at risk for learning disabilities. The title of his presentation today is Latent Class Analysis of Children with Math Difficulties and/or Disabilities. Are there cognitive differences? A little bit different than the sub. You want me to go and change that in the slide? No,
No,
just kidding. All right.
You said you randomized them. Thank you for allowing me to be part of this panel. Mine has no videos of kids or anything like that, so it's going to be a little bland. But in this, I'm going to look at defining kids with math disabilities. And I have three primary questions in my analysis of this data set. I want to know if there's a good model that supports a discrete class of kids who have math disabilities or math learning disabilities that's independent of reading problems. When I use the common cutoff points as referred to in the literature, usually between the 11th percentile and the 25th percentile, the literature seems to suggest these are kids with math difficulties. And below the 11th percentile, it depends among different researchers, but below the 11th percentile are kids with math learning disabilities. And so my second question would be, what sort of predicts these classes if they sort of emerge in my data set? And then if I change my cutoff points, do I have some different variables that are going to predict that particular latent class? My assumption is that even though we use cutoff scores, there's a lot of heterogeneity within that particular population we come up with. And even though we look at these as continuous variables when we talk about math, there could be some hidden groups or some hidden subgroups within that particular population. Also, there's a high probability, I think, in some of the data sets I've worked with in the past, that you're not necessarily going to get a kid with math disabilities completely independent of reading, but we can look at that to see if we have a good model that fits that. And then there's some advantages to latent class analysis. I might say up front, latent class analysis is an exploratory procedure. I mean, there's just stuff coming out. There's a number of indices that you could use to come up with a number of latent classes, but it is clearly an exploratory procedure. In my data set, so I have my manifest variables. I have almost 450 kids. I'm focusing on grade 3 in this particular case. I'm looking at calculation. As you know, you have to, these are my manifest variables. These are the variables that I'm going to use to determine my latent classes. I have the wide range achievement test, the Wyatt, and then I have 4 problem-solving measures. And the reason I have 4 in there is because you get a sort of a different response from a kid who has to read a problem and calculate the answer, versus when you give them a problem and they have to do it in their head, versus if they see a picture and sort of point to what the answer would be in the word problem. So I have a larger representation of word problem or story problems. Then also in my latent class analysis, I'm using variables in reading. I'm using a wide range achievement test, which is basically a word recognition test. And then I have the test of reading comprehension. And then I have a fluid intelligence measure. In my predictor variables, so I want to come up with see how many latent classes I come up with. So I showed you those variables, but I want to be able to see if these variables predict these latent classes. And so I have an area of phonological processing in general. I have what we call simple span tasks, which are digit words and pseudo words. And so you're going to see multiple tasks because I don't think you can rely on any one task. You have to create a latent variable for measurement issues. And so you can see I have 3 for short-term memory, and I have 2 for naming speed. And then I'm looking at domain-specific measures to see if they predict. And I have a task that I've used over the years where you test kids to see what they can pull out of a word problem in terms of the propositions they attend to. And then I have a line estimation task, and you can have a line, and they put the number where they think the number goes in this particular line, and also you can manipulate the line length if you want, which we've done. And then a magnitude judgment class task, where how quickly out of an array of numbers, which is the largest, which is the smallest number. So we have sort of domain-specific measures. And then executive processing, I see that as a fragmented kind of activity. In my research, executive processing usually focuses on updating or an inhibition kind of activity. It's usually, when you do a regression model, it's sort of the residual variance that's left over after you take storage out, so it's sort of controlled attention, if you will. And so in executive processing, I have a battery of working memory tasks, and then I have inhibition measures that I've used over the years, where you have to, you give a kid a task where they have to write the letters of the alphabet as quickly as they can in 30 seconds in order, and then you tell them to do it out of order, and as quickly as they can do that. And so use a number of measures to get off of that in terms of inhibiting what would come rather automatic. And then I have a visual spatial working memory task. There are different indices used to determine latent class, and I think this is highly exploratory. But a colleague of mine at the University of California in Santa Barbara, Karen Nyland, who's done probably the most cited work in terms of this, she sort of suggests the Bayesian information criterion. And what you're looking for is the smallest number. So if you go over to LC3 and look down, you see the BIC, and you see right up when you get to LC4, it begins to increase. So you get a bump in your index. And so usually at that point, you determine if that's the best fit overall. It doesn't always coincide with all the other indices that you could sort of look at, but in this case, it was a pretty good fit. And this is when I take those manifest variables I showed you in terms of calculation, word problem solving, and reading and so forth, and I just make a cutoff score, kids below the 25th percentile on the normed reference measures, and above the 25th percentile. And doing that, how many latent classes do I come up with across these particular groups? So I came up with 3 latent classes. And you can also do that for the 11th percentile. If you look, I just put in bold where the BIC index is. And so, again, I had 3 latent classes. Then you look at basically the items that are really help you interpret what the latent classes are. And so up above, you have the gamma values. In other words, that's the proportion of representation in the sample of kids who would be at that particular latent class. For our discussion, let's just look at latent class 2, which is the risk group here. So if I use the 25th percentile cutoff, about 15% of my sample is kids at risk. And if I go over to the 11th percentile cutoff point, it's about 10% of my sample. It makes sense because you're basically lowering your cutoff point. Looking at the variables, going down, let's take the 25th percentile coming down with latent class number 2. You can see here you have a probability. So it's the probability that the child would get below the 25th percentile. And so you can see here on the Wyatt test, 0.82 is the probability of getting that is about 80% chance that that population, that group is going to have a low score below the 25th percentile in calculation. There is no, in the literature, there's no point of where the cutoff point should be. So I just put that in using any other publications. There's just not anything what's meaningful. In terms of word problem solving, going down that same column, you can see pretty much latent class 2, all of those areas have a high probability of being below the 25th percentile. And then you have, in terms of reading, comprehension, 87% chance of being in that particular, having that below the 25th percentile. And then word identification, not so much in terms of high value, and not a high value in terms of the Raven test. So you can take that, and then you can begin to look at the scores of the kids. So if I use the 25th percentile cutoff in this population of almost 450 kids, third graders, what do their scores look like in terms of standard scores? And you can see they're extremely low. And so we didn't a priori cut out any of the kids we had in the schools that we tested. We tested all of the kids, and that's in our data sets. We didn't remove any outliers. But you can see here, in terms of LC2 latent class, it's below, clearly below the 25th percentile in calculation. Certainly, we've got kids that can barely even do the word problem solving at all under math problem solving. And then in reading comprehension is low, pretty much around the 90th percentile for word identification, and pretty much average in terms of fluid intelligence. So that's what our data set looks like. If we use 11th percentile, it just drops the scores further. We still have, again, 3 latent classes. Again, you can see the scores. These are standard scores, so almost non-performance in the area of math or story word problems in terms of the TOMA, the WISC, which is an arithmetic subtest from the Wechsler where you give the problems out loud. In the CMAT, Comprehensive Math Abilities Test, the story problems, you can see that's extremely low. We got some kids pretty much non-performers. And then key math. In the reading comprehension, you can see extremely low in terms of reading comprehension, and then, of course, word identification. All right, now we have 2 groups then. So I broke it off the 25th percentile, and I can certainly do a meta-analysis of the literature that uses the 25th percentile. How many studies use that? Lots of studies use the 25th percentile. And so, but when I change the 11th percentile, you get a group that moves out, and I think technically you can argue that's probably math disabilities group. Or math difficulties group, I'm sorry. It's a math difficulties group, the one that would move out after you drop it down to the 11th percentile. And then you have the kids that are stable. It doesn't matter where you put the cutoff point. They're going to just stay in that particular classification. Well, there's no, even in latent class analysis, there's no studies, a couple studies have been done in power analysis, but predicting power. So what I did here is I just calculated effect sizes between these 2 groups. So who are the kids that transition out? If I drop it down the 11th percentile, who are those kids that are kind of in the middle with the math difficulties? And you can see the effect sizes here. So pretty large effect, so it's just a Hedges G. Basically, look at the last column there, come down in terms of the effect sizes. The interesting thing is in the area of reading, large differences between kids with math difficulties and math learning disabilities. And overall, hardly anything in terms of fluid intelligence. And clearly, there isn't that large a difference except on the TOMA, which is you have to read the problem and solve it in terms of differences between kids with math difficulties and math learning disabilities. So reading seems to be fairly critical. You can predict your, I can take my cognitive variables, and these are going to be latent variables. I'm going to predict the latent classes, so I'm using a logistic regression in terms of predicting these latent classes. And you can look at it when you use the 25th percentile cutoff, what are the variables that uniquely predict the latent class? So this is a simultaneous entry of the variables. And so you're getting what's unique in variance in this. And you can see here when I use the 25th percentile, you get in the domain-specific area, I mentioned the task where they have to kind of tell us what propositions they attend to in a word problem, has significant loading. And you have the estimation task is significant, and then you have the executive, the working memory task are significant. So those are 3 significant things that emerge when you use the 25th percentile to determine your latent classes. If I use the 11th percentile, we get a little bit more information. We also find difficulties, as you can see over there, in short-term memory, and also in terms of naming speed. The component one, again, that task where I ask them to tell me, point out or identify the propositions they're attending to in a word problem. And estimation emerges. And then again, the executive part of working memory emerges. And then we have also the visual spatial part emerges. So these each uniquely predict the latent class. Okay, then I can begin to look at comparisons between the kids who would be average achievers, that's latent class 1. Latent class 2 is our risk group, and then latent class 3 is the kids that are poor problem solvers. And again, you can begin to look at the effect size differences on each of these particular cognitive variables. And clearly, kids LC2, latent class 2, the risk kids, this would be the ones that are fairly stable when you use 11th percentile to stay there. Basically, very high effect size differences between them and average achievers. Not so, and then you also begin to see the differences over when you compare this risk group with kids who are just poor problem solvers in terms of effect size. Okay, in 1 minute, basically what I found is you can identify a hidden group of kids with math problems within this heterogeneous group, and you can see I had quite a distribution of scores. What I didn't find was a good fit to the data with kids with just math problems independent of reading problems. In terms of cognitive modeling, you can argue domain-specific areas like numeracy and so forth are probably unique predictors. We found some of that, but we also found the executive system very uniquely predicted these latent classes. The implications is, I think, in this data set that we have, we can contribute somewhat to the literature on identifying a discrete group with math problems. We can't, at this particular point with this data set, identify independent of reading problems. The limitations of this data set are numerous, actually. We have not validated a particular cutoff point. We're just using cutoff points that are used in the literature to identify this particular population, and then from that we determine if discrete groups emerge above or below that particular cutoff point. We didn't look at the stability of math performance across multiple grades. We haven't completed a latent transition analysis at this particular point. We didn't remove the outliers. I mean, there's some kids when they got a word problem in front of them, they had difficulties reading, so obviously they're not going to solve the problem. You can see the scores varied quite a bit there. And there was no intervention information that we've tied to this particular presentation. That's it.
Thank you. Questions? Where to go?
Yeah. Oh, yes.
In a few of the presentations today, I've heard about identifying math disability with reading disability and are there different subgroups there. But has the research gone into the area of looking at early literacy interventions when we see that there's been normalization or compensation? Does that impact math outcomes?
You know, I'm being honest, I don't know that literature that well to know in terms of what reading intervention does in terms of systematic, evidence base and how that would transfer over to another domain such as mathematics. I would say there'd be a good connection between reading comprehension and math problem solving. In fact, I found that in my literature is one of the best predictors is reading comprehension. So I would find in terms of that as such, but I can't cite what the effect sizes across all those studies might look like in terms of transfer. I just don't know that literature.
Okay, thank you. Our next presenter is Lynn Fuchs. Lynn is the Dunn Family Professor of Psychoeducational Assessment and Human Development and Professor of Special Education and Psychiatry at Vanderbilt University. Her research focuses on classroom-based assessment methods and intervention procedures in reading and math, comorbid learning disabilities across word problem solving and reading comprehension, and across word-level reading and calculation skill, as well as sources of individual differences in mathematics development and responsiveness to mathematics intervention. Title of her talk, hope I have the right one, Does Embedding Language Comprehension Instruction in Word Problem Intervention Improve Word Problem Outcomes?
Hi, everybody. So how much time do I have? Dan?
Time's up. No, sorry, I just couldn't, no, you're fine. You got
Okay.
approximately 12.5 minutes, sorry.
Okay,
for
so I'll jump right in. You can see who the Major contributors to this study have been, and I want to make sure to acknowledge NICHD as the funder of this study I'm going to tell you about. So the first question that we are addressing here is word problems and why focus on word problems at first grade. So first grade number knowledge intervention with speeded arithmetic practice dramatically improves arithmetic achievement gaps, but at the same time, the word problem achievement gap widens dramatically. And this is problematic because word problems represent a major emphasis in almost every strand of the math curriculum. And word problem performance is a strong predictor of wages in adulthood. But early math research has focused dominantly on number knowledge and arithmetic, with only a minor focus on word problems, usually in the service of helping contextualize arithmetic problems for children. So our second question that motivates this research is why focus on language comprehension to improve word problem performance? Based on the work of Kinch and colleagues, word problem solving is an interaction between math problem solving strategies, which rely on reasoning and working memory, and language comprehension processes. And when faulty math problem solving is computationally modeled, with math problem solving errors versus language comprehension errors, correct problem representation depends more on language comprehension, and changing words in only minor ways dramatically affects accuracy of problem solving. Yet the common assumption in schools is that students have the necessary language comprehension for understanding problem statements and building an appropriate problem model. For at-risk children, this assumption is shaky, which prompts the question, do we need an instructional focus on language comprehension processes as well as mathematical aspects of word problem solving? So the next question is, well, why embed language instruction in word problem intervention instead of providing more conventional language therapy? Well, language therapy improves oral language comprehension, but transfer to academic performance, both in reading and math, is limited, despite a strong association between language comprehension and academic performance. Also, transfer from language therapy to academic performance may be especially challenging for at-risk children who have an inadequate foundation of academic skill to which they might transfer their improved language. And at-risk children experience substantial difficulty with transfer. This argues for language instruction in the context of direct skills intervention, and that's the approach that we adopted in the present study. So I also want to clarify, we've heard a lot about explicit instruction. I'm going to use the term direct instruction in this talk because when I say direct instruction, I mean teaching word problems directly. When we're doing any kind of teaching in this study, whether it's on language or on math problem solving strategies, we're teaching explicitly. So our approach to math problem solving strategies relies on schema-based instruction, as Karen mentioned this morning, which explicitly teaches step-by-step strategies to reduce demands on reasoning and working memory. And this includes strategies for understanding word problems as belonging to word problem types, as well as strategies for building word problem models. And the child uses these strategies to name the problem type, represent that problem type with a number sentence, enter relevant quantities from the word problem statement into the problem model while crossing out extra numbers, and solving for the missing quantity. So there's an example of a combine or total word problem Kathy has 5 pencils and 3 erasers. Pamela has 7 pencils. How many pencils do the girls have in all? And here the child decides this is a total problem and labels that with a T to reduce demands on working memory. Writes the problem model number sentence to go with that problem type. Fills in quantities from the problem statement into the number sentence and solves for the missing quantity. Now, I just want to point out, since keywords were mentioned, and because in all it happens to be in this problem, that the language that we're teaching the children and the problem model does not determine whether children add or subtract, because the missing quantity can be any place in the number sentence, and that's what determines whether you have to add or subtract. So there is a screenshot of a first grader solving a total problem. 4 girls and 3 boys are playing on the swings. They swing for 10 minutes. How many children are playing on the swings in all? And there you see the child's work. Well, there's a little T over toward the child's left hand. My husband will be amazed that I got that right, I think, left or right. There's the number sentence. That's the problem model. The quantities are being filled in, and the child solves for the missing quantity and labels the answer. So, as I mentioned, we're also embedding language comprehension instruction, where our focus is on word problem vocabulary and language constructions. So when we are working on combined problems, what we're focusing on in the language instruction is joining words and superordinate vocabulary, like animals equals dogs plus cats, where when we're working on compare problems, we are working on compare words and the difference between adjective ER words versus verb ER words. In change word problems, we're working on cause-effect conjunctions, implicit quantity change verbs like cost or ate or found, and time passage phrases. And we also address confusing cross-problem type constructions. For example, more than versus then there were more, as well as tricky labels. So in this study, we had 3 purposes: to increase understanding about the role of language comprehension in word problems and arithmetic, assess the potential of embedding cognitive training, and we're using that term broadly to include things like language comprehension, within direct skills intervention, and to address word problem difficulty early in first grade when individual differences in word problem skill are growing rapidly. So a brief overview of the study: we defined risk as low arithmetic and low math concepts and applications at the start of first grade. Students were randomly assigned to 4 conditions: word problem intervention with embedded language comprehension instruction, number knowledge intervention, which I'll explain in a minute, and a control group, which was the school's typical program. Each active condition lasted 15 weeks, 3 sessions per minute for 30 minutes per session. And each of the 3 active conditions included 5 minutes of speeded strategic arithmetic practice so that we could kind of control for a focus on the arithmetic that was required in word problem solving. So 400 children will enter this study. I'm going to tell you about results to date on the first 159 students who've completed. And a word about that number knowledge intervention condition. We were asking the question, is transfer from arithmetic to word problems sufficient to support word problem development? And here we provided explicit instruction on number knowledge, relations, and principles with a strong focus on number families and decomposition of number sets, and strong reliance on the number line manipulatives and games to reinforce the mathematical ideas that we were teaching. So our findings to date. On arithmetic, all 3 intervention conditions are outperforming the control group. You see what the effect sizes are for each of the 3 conditions versus the control group. So the way you read this, for example, is the number knowledge condition versus control. The effect size between those conditions on the outcome is 0.81 standard deviations. On the word problem outcome, both word problem conditions are producing significantly better outcomes than number knowledge and the control conditions. But differences between the word problem and the word problem plus language conditions are not significant. The p-value is 0.06. If the effect size of 0.37 between the 2 word problem condition holds, then that will be significant with a full sample. And we also look at post-treatment word problem language, where only the word problem plus language condition is outperforming the control group, and in fact, it's outperforming all of the 3 competing conditions. And there you see what the effect sizes are compared to the control group, and at the bottom you see what the effect size is between the 2 word problem conditions on word problem language. We also ask whether end-of-treatment word problem language mediates the condition effects on word problem solving. Each model controls for pretest word problem skill and arithmetic skill. So the left-hand triangle shows you the effect or the model for number knowledge versus control group. The next triangle, word problem intervention versus the control group. And then at the bottom, the word problem plus language condition versus control group. The descending side of the triangle shows you the B path, which shows you that there's a relation in all 3 contrasts, indicating that the stronger your word problem language, the stronger your word problem solving accuracy. But if you look at the ascending side of the triangle, you see that only the A path for the bottom model, word problem language versus control group, is there a significant effect, indicating that the intervention is significantly improving word problem language, which I talked about in the last slide. When we look at the indirect effect of the intervention via word problem specific language on the outcome, only the word problem plus language condition shows that indirect effect, a significant indirect effect. So the word problem plus language is having an additional contribution to word problem solving outcome, and the mediation or indirect effect indicates that part of that total effect is attributable to the effect that occurs via improved word problem language performance. So our preliminary conclusions are these. On word problem solving, number knowledge intervention does not provide added value over the control group. The effect size was 0.10. Despite the number knowledge intervention produces significantly better arithmetic performance, where the effect size is 0.81. And this raises questions about whether transfer from arithmetic to word problems is sufficient to support word problem development. On word problem solving, embedding language comprehension instruction indirect skills word problem intervention appears to offer added value over word problem intervention alone. Here the effect size is 0.37. And the mediation effect indicates this added value occurs via embedded language comprehension instruction. So results strengthen evidence for the role of language comprehension in word problems and suggest promise for an expanded intervention framework that embeds training on language and perhaps other cognitive processes within direct skills intervention. And results in terms of this meeting also suggest a connection between math problem solving and reading comprehension via language comprehension. And in an RCT that is just getting underway, we are asking the question, does a link between word problems and reading comprehension via language comprehension provide direction for understanding comorbid difficulty between word problems and reading comprehension? This is an experimental manipulation testing the effects of instructional scaffolding that connects word problems, reading comprehension, and language comprehension in a sample of students with comorbid difficulty. And this is an NICHD-funded study that's one of the learning disabilities hubs. Here we have 3 study conditions: a direct skills word problem intervention with embedded word problem language instruction, a direct skills reading comprehension intervention with embedded reading comprehension language instruction, and a control group. And we're conducting 2 tests of what we call the comorbidity hypothesis. The first concerns whether reciprocal effects occur for word problem intervention on reading comprehension outcomes, speaking to the question that was asked just a few minutes ago, and whether reading comprehension intervention provides reciprocal effects on word problem outcomes. And then the second part of the comorbidity hypothesis test is whether language comprehension improvement serves as a mediator of those reciprocal effects, which would indicate that language comprehension is a common process linking word problems and reading comprehension.
Great. Thank you. Is there time for a question or two?
Yeah.
Did you look at or tease out students who have decoding only problems with comprehension problems? In other words, if the problems were provided to them in a moral way, would they have language comprehension skills? And was that something that you looked at as another variable?
Yeah, so we do have a measure of word reading. We don't have a measure of non-word word reading, so we don't have decoding measures. And that's the math study. But in the study that's just getting underway, we hadn't thought to include a measure of decoding, but we might do that. That's a nice idea.
Okay, well, it says that there's a break coming, but you may not have seen in fine print. I'm listed also as the discussant, not the chair. So I will make several remarks to try to put some of the results that you've heard in a larger context, and I'll try to do that in 5 minutes standing on one leg. All right. Basically, I'll be talking a little bit about working memory, attention and cognitive flexibility, language and reading comprehension, and mathematical learning difficulties and disabilities. Again, wanting to present more of a context, we didn't necessarily have a more plenary talk on math cognition and math learning disabilities per se. To start from the last talk, since that's fresh in your mind, quotes, as Lynn just summarized, based on the work of Kinch, had hypothesized there would be an interaction between language comprehension and math problem-solving strategies, and indeed her results provided evidence for that, suggesting a connection between math problem-solving and reading comprehension by way of language comprehension. The broader context here is that there are a number of ways in which there can be linguistic influences on math, and briefly using a framework by Ann Dowker and Hans-Christoph Neuwerk from last year, where they outlined 7 different categories, and mention a few of these briefly, and Lynn's work in that context. There's the lexical composition of number words. So, for example, as many of you would be aware, in East Asian languages, number words for numbers beyond 10 are more transparent than our English number words. So, in other words, 10-1 is more transparent with respect to standing for 11, in contrast to the irregular word 11. So that results in usually more rapid acquisition of the base 10 concepts. Semantic, the meaning of number words, meaning of words in general, especially those that relate to math and arithmetic in particular. So in Lynn's study, part of her training involved focusing on the meaning of more, fewer, and other comparison words. Another example where that can either facilitate or inhibit successful problem solving is if the required mathematical operation is not consistent with the words in the text, you'll be slower at learning. So if you have to add something, then the word more should be associated with it. And if subtract, it should be the word less. So let me give you an inconsistent example. Jimmy has 6 more cookies than Billy. If Jimmy has 9 cookies, how many cookies does Billy have? So I use the word more, but now you have to subtract. That's inconsistent, and you're slower and less efficient at solving that problem. Syntactic. Here we have the grammatical structure of languages beyond word-level influences. You may not be aware of the label, but what's known as grammatical numbers. These are morphological influences on numerical processing, and it's typically characterized by singular, plural language markings. For example, if I talk about cookie versus cookies, that allows you to distinguish between sets of 1 or sets of 2 or more. Phonological, which you've heard a lot about here, while there may not be as direct an influence of phonological factors on some aspects of arithmetic processing. I'll give you an example with students with specific language impairment. For them, and they do have phonological processing difficulties, that can adversely impact their numerical transcoding, where they're forming association between spoken number words and written Arabic numerals. Write down the number 7. Okay, so you hear 7 as the number word. There are a number of those kinds of transcoding operations. So phonological processing for these students can adversely affect them. I won't get into the visuospatial orthographic and conceptual. The last one is other language-related skills, such as a verbal working memory, and cognitive skills related to language representations. And this, again, is where part of Lynn's work fits with respect to the language comprehension skills being needed to build an accurate representation of a word problem model and thereby reduce the demands on working memory. If you're interested in more details about language influences on mathematical cognitive development and mathematical cognition in general, I highly recommend a forthcoming book on language and culture, mathematical cognition. It just happens to be edited by myself, David Geary, and Kathy Mann Kepke. We're selling it outside along with Phil's your executive function test. No, it's not out yet, sorry. Well, now, a few more minutes. Swanson, Lee talked about several things. What I haven't read is his statement about the finding of a latent class of children with math disabilities or math learning disabilities. Completely independent of reading problems may be quite low. Estimates made by others in the past, I think introductory paper by Brett Miller, who's here, and Kathy Mann Kepke and JLD a number of years ago, showed that estimates of the prevalence of co-occurring math and reading disabilities range from 16% to 66%. We still, maybe that's being narrowed now somewhat, but again, Lee's findings here are interesting and one needs to build upon that and get more specifics about how that affects our prevalence estimates. I wanted to mention that there are some other approaches. One example by Bartlett, another data-driven approach to identify here within a group of students who have already been considered a clinical sample with math learning disabilities, gave them a battery of various cognitive measures, and using hierarchical clustering, revealed 6 different clusters of children with math learning disabilities. A weak mental number line group, a group weak in the approximate number system, spatial difficulties group, an access deficit group, no numerical cognitive deficit group, and a garden variety group, okay? And so, as they said, this suggests there may be different cognitive subtypes of MLD that can be derived from data-driven approaches to classification, and strengthens the notion that MLD is a heterogeneous disorder. Philip Zelazo, I happened to pull out the definition, and I think was an IES white paper recently, which I found quite interesting. It said a lot with respect to the overview of executive function skills. As he mentioned, attention regulation skills make it possible to sustain attention, keep goals and information in mind, refrain from responding immediately, resist distraction, tolerate frustration, consider the consequences of different behaviors, reflect on past experiences, and plan for the future. Well, students with learning disabilities generally exhibit executive function difficulties across the board, albeit to differing degrees that most likely depend upon age, specific type of LD, severity of the learning disorder, etc. I cited myself, personal communication, that's what I told myself. Okay. So now, much of this research in what he called the cold cognition is focused on working memory, inhibitory control, and cognitive flexibility, although typically from the standpoint of the Baddeley and Hitch multi-component model. And one of our attendees and speakers, Marcia Barnes, I had concluded a number of years ago with her colleagues that in general, the findings from studies of preschoolers, elementary school children, and adolescents suggest that executive and visual spatial skills may be recruited for learning and application of new mathematical skills and concepts, whereas the phonological loop and verbal working memory may come into play after a skill has been learned. So again, there are developmental changes as well as changes over the course of learning, and these, it's important to make these distinctions. Well, I figured no one had said much about the brain other than the ERP data, so I wanted to at least put that up, and I should say one or two things about it, and that's it, maybe one other slide. So most people have thought about a math learning disability or dyscalculia as being comprised largely of a core deficit in number sense, basically non-symbolic judgments of quantity, and subserved by the intraparietal sulcus. But as Fias and colleagues have suggested a number of years ago, there's a great deal of connectivity to other brain regions, whereby when presented with a certain number form, the IPS again subserves judgments of immediate judgments of quantity and the approximate number system. But there are connections to the working memory system and cognitive control, as well as to episodic and semantic memory, especially once you have to retrieve math facts, and to the attentional control system. Recently, Vinod Menon and colleagues have shown that as compared to typically developing children, children with mathematical disabilities showed hyperconnectivity of the IPS with this bilateral frontal parietal network. And the aberrant connectivity patterns actually accurately discriminated MD and TD children. So what's intriguing about this is it might provide the possibility of using the IPS connectivity as a brain-based biomarker of mathematical disabilities. And they hypothesized that increased hyperconnectivity, that's mostly what I'm focusing on here, may limit flexible resource allocation, contribute to aberrant recruitment of task-related brain regions during numerical problem solving in children with MD. And most recently, it's been shown that if you use an intensive number line training, that abnormally high functional connectivity in people with developmental dyscalculia can be normalized on the neuronal level. They concluded that this kind of training can lead to a reorganization of interregional task engagement. So more than you needed to know, and I'm not sure there's time for questions, but maybe one if you want to have a break.